the things we talked about in class, which quite literally is only two things. Kinetic energy, 1/2 mv squared, work either the integral or an algebraic computation. And then the concept that total work is equal to change in kinetic energy. These are the things we've talked about in this class so far when it comes to work. And that's what we would use probably for questions 1 and 2. Question number 1, how much energy does the ball have? The ball only has one form of energy that we've been talking about. Those of you who had physics last year know that's not true. It has two forms of energy right now. It has two forms of kinetic energy. But for us right now, we're only dealing with one, and that's translational kinetic energy. So the kinetic energy it has right now is 1/2 mv squared. So 9 joules of energy. The total work that has to be done on the ball bringing it to rest has to be equivalent to -9 joules. If I want to bring the ball to rest, I want its final kinetic energy to be 0. So the total work would have to be equal to the change in kinetic energy, which is going to be 0 minus 9, or -9 joules. How far up the ramp will it go? Well, for that one, you have to consider what's doing work as the ball rolls up the ramp. I can only think of 2 forces acting on the ball that legitimately have anything to do with this problem. There's the possibility of a third if you want to consider friction is necessary for the ball to roll up the ramp, but the friction doesn't do any work on the ball either. The only thing that does work on the ball is weight. Weight does work on the ball. Now, to figure out how it does work on the ball, probably should look closely at the ramp. The ball is on the ramp. The weight's going to be acting this way on the ball. Now, there's a variety of methods you could approach this problem. You could work this problem in terms of the components of the weight down the ramp. I would encourage you not to. It's a less work just to consider the weight. Meaning, I'm going to use the definition that force times displacement times the cosine of the angle can give us the work done. I'm also going to point out that the force here is the weight of the ball, 20 mg. We don't know the displacement, but we do know that the displacement is in this direction up the ramp. That's the direction of the displacement. And we know that the force is straight down, so this is the angle we want. Now we have to figure out what that angle is, which is not particularly hard given that we have 40 degrees at one end of a clear articulate triangle. That means this has to be 50 degrees. What does that leave this? Yeah, it's got to be 130 degrees. It's got to be the supplement. So this will be the cosine of 130 degrees. Now, some of you probably did this differently or didn't do it like this. That's fine. But this is the way that I'm doing it to demonstrate that work is always going to be based on the angle between the displacement and the applied force. But like I said, you could have done this from the components of the force, mg sine theta. That would have worked. You'll get the same answers, promise. This, of course, does give us the negative sign that we need. The work has to be negative. And we're going to set that equal to -9 joules, which gives us a displacement of what, like 70 centimeters? Something like that. Level of difficulty here? Low? Probably, I hope. All right. Any question about this? So we're going to move on from here. I want to talk about a couple things today, but I want to make sure that we are working towards a solution, and I also want to make sure that you guys are having your questions answered. Is there anything in the homework that you need me to address so that you'll be in a better position for tomorrow? I will handle a question or two. So this quietness. We're going to have to consider that our force is not constant. So this is number 23 in the textbook. I think it said qx squared is the force, where x represents the displacement. So whatever's happening to our object, which it doesn't matter what it is, the object itself is experiencing some force that is a function of displacement. Is that okay so far? There's a number of ways I could talk to you guys about this. And we are assuming that the object begins at 0. So we know the force at the original position is 0. Something must push it away from the original position for there to be a force after this. And then the force is growing at a pretty quick clip, as it is a squared property. Now, I can explain this two different ways. And one of them is meant just to ensure that I have everybody's kind of cooperation. This is force versus displacement. It's quadratic. So I'm just drafting a quick quadratic. And we are interested in how much work is done as it goes from 0 to a location D. That would be the area under this graph. Now, you can't compute this area using simple geometry. But I'm bringing this up because there's every reason to believe that I could give you a graph like this. Something goofy or something like that, where you could compute the area using geometry, and this area would be the work. I mentioned this in passing. I haven't given an example, but this is a plausible way to do this problem if you could find the area under a curve. Well, we can't. Not easily. That's why we have tools, and the tools we have are calculus. So I'm going to use the calculus tools, and that's the definition of work based on the integral, which sums it as we move the object small increments at a time. I will point out that although not all of you are in calculus, I'm going to expect that we are acclimating a little bit at a time. I will not be testing you on calculus-related materials until second semester, but that doesn't mean that we won't be doing a little bit of calculus here and again. In April, though, everybody will be fully acclimated and we'll have to do problems like this. So you have time, and I'm giving you little practices. So here's our first practice for this example. We have an expression for the force in terms of the displacement. So the first thing I would do is tell you to substitute into your integral your expression for the force. Next, you have to evaluate the direction of this force relative to the displacement. That's a very fancy way of saying, is the force in the direction the object's moving or not? Do I have to put a cosine in here? We were told in the problem that the force is in the positive x direction. The object is moving in the positive x direction. So that means cosine of 0 degrees. But make sure in your notes, you give yourself a little bit to remind yourself to evaluate the direction of this force versus the direction of the displacement. It's possible to have an integral that requires you to deal with that angle, where the angle is what's changing and not the force. I can put a simple example on the board if you need one, but I just want you to be aware that they could do that. For those of you who are learned about this, you know what I'm going to say next, but evaluating an integral is really kind of a two-step process. but the first step is the one that probably you'll have the most investment in. The first step is finding the antiderivative of the integrand. That's the part between the special fancy s and the dx or d whatever. Ours says dx because our object's position is located as in terms of x. If it was in the y direction, I'd probably put dy there because it would be moving in the y direction. This is just supposed to be a small change in position, so it represents whatever variable is supposed to be about position. The squiggly line is a placeholder to remind me to sum and to put my limits in, because the second part of an integral is to apply your limits. So we're going to do the first part, which is to find the antiderivative of qx squared. Now, there's not a whole lot for me to say here, except that this is a polynomial, and we're taking the antiderivative with respect to x. So the q doesn't matter. The q is a constant. Any variable that is not x, we can ignore or treat like a number. So you could treat this like 2x squared and be asked to figure out the antiderivative with respect to x. The q would be treated like the 2. I would just kind of ignore it and deal just with the x. Same thing here. And we've taken this antiderivative. If you'll recall, you add 1 to the exponent and you divide by the new exponent. That's the antiderivative. So for polynomials, which is why I gave you a polynomial one, when you're doing the antiderivative, you add 1 to the exponent and divide by the new exponent. Ours doesn't have a 2 in front of it, though it has a q. So I will have a q divided by 3, x to the third. That is my antiderivative. So step 1 of calculating the integral is done. I put this bar, or if you're in calculus, you put a set of brackets, and I put the limits at the outside edges of that bar to remind myself that I have to do the second part of an integral, which is applying the limits of integration. Now, we did this a little bit when we did antiderivatives. We talked about the initial conditions. That's what these are, the initial conditions. All we do here, though, is put in each of these for x and subtract them. The top one goes first, and the bottom one goes last. So this is q thirds d cubed minus q thirds 0 cubed. So at the end, the work done will be q thirds d cubed, and that's the answer. This will not be on your quiz tomorrow. As I said, I am not testing you on calculus this semester, except for what we did already. But this is what you are expected to do. Okay? I will answer one more homework question. Yes, sir? Problem. So my expectation is those of you who have already had physics should have been able to do this problem. It wasn't terrible. But for you guys who are fresh to it, it was probably a challenge. So the work done in compressing an ideal spring, we've talked about it already, is 1/2 kx squared. We kind of showed the calculus of that earlier. But they're saying that we have this real spring that has a force of, it was k delta s plus q delta s cubed minus. So just like regular Hooke's law, they're both negative to indicate that the force is in the opposite direction of the displacement. It's a reminder of that's why it's negative here. Now, the work done on this spring in compressing it 0 to 0.15 meters. It's telling us that we are compressing the spring 15 centimeters. I'm putting the limits of integration into my problem. And I'm going to go one step further, and I'm going to put in the numbers for K and Q, because I think for folks who are just coming to this for the first time, it might be easier. So 250s minus 800s cubed ds. Now, I am concerned that some people would not have known to do what I just did. Change these delta s's to just s and put a ds out here. But our definition of work looked like this, with f and x being vectors. This was telling us from the beginning that we were to put in the expression for f and put it in terms of the displacement. They're using s for the displacement of the spring. The delta represents the actual displacement of the spring, the 15 centimeters. But I have to put it in this form. So I put where it is, and I put the ds here because we're trying to tell the calculus that we're compressing it a little bit at a time and figuring out how much force is necessary for each step. That's what this calculus states. Once here, however, I should also evaluate the meaning of the negative sign, but I'm going to leave that to the end for right now because it doesn't really affect the problem. In fact, I could pull it out front and make both of these positive so that you're not distracted by it. Because just like any other parentheses, you can use any form of algebra with calculus. I could actually pull out a common factor between the 250 and the 800 if I'd like to. I'm not going to. I'm just going to leave it like this, but you could. But I mean, 250 and 800 share some common factors. Now, again, this is our integrand. We are integrating it with respect to ds, which makes s the variable. The numbers are constants. And we're going to take the antiderivative of each term. There are two terms. So the first one is s to the 1 power. So this will be 250 over 2 s to the 2 power. The next term is s to the 3 power. So this will be 800 over 4 s to the 4 power. Add 1 to the exponent and divide by the new exponent. It's a polynomial, so I take it term by term. Don't forget my negative sign. And don't forget my limits. Now, I do have to evaluate this now, meaning I have to put in the limits. Can everybody recognize that putting in 0 is going to zero out this thing? So putting in the limits just means putting in the 0.15. But I'm going to be thorough and say that this is 250 over 2.15 squared plus 800 over 4.15 to the 4th, all minus 0 plus 0. Put in both limits and subtracted them. I'm being thorough, and it's killing me. All right, you have calculators. You tell me what this is. You have an answer?
I do have the answers, but I had a question. If you were doing like an FRQ regarding this, would you have to put in the second limit even though we know it's 0 or no?
They're just, if you're just evaluating it, they're not going to be looking at your work like that.
Okay. But if you need to know.
I would like what this is, yes.
Well, the first part, 250 over 2.
Just give me a number.
2.8125, and then it would be adding with 0.10.
Oh, I want the whole thing. I don't care about the individual terms. People can do arithmetic. Thank you. Jeez. I'm not going to worry about people's arithmetic. If you can't do that, then you didn't make it out of elementary school. Well, maybe elementary, but you didn't make it out of Algebra 1. So this is the amount of work done compressing the real spring. Yes, ma'am.
So why did you add the 0 plus 0 at the end?
I didn't add it. I subtracted it. And I subtracted it because I have to put in the top limit of 0.15 into each term. And then I have to subtract putting the bottom limit into each term. Okay? But you subtract the bottom limit from the top limit. You're welcome. I have to assume that this is in joules because it's work. Now, it's negative. You have to be careful about what the negatives mean here. This means whatever compressed the spring lost this much energy. How much energy did the spring gain? This much energy. So when we talk about negative and positive when it comes to a spring, you have to remember that a spring can't compress itself. It is being compressed by an outside agent. The outside agent has to lose this energy in order for the spring then to gain this energy. So I'm not going to split hairs about this negative sign. If I want to know how much energy the object that compressed the spring lost, it's this amount. If I want to know how much energy is inside the spring right now, it's this amount. Does everybody follow that okay? Because right now I'm going to say the work done in the ideal version of this spring is 1/2 kx squared. We talked about this day before yesterday. So I can skip not having that s cubed term for a minute. This is the ideal spring amount of energy. And again, I don't even have a negative there at all because the work done really depends on what I'm talking about. But ultimately, this will be 1/2 times 250 times 0.15 squared. I will need this. Sure? That's going to be 2.8 joules. Why is it negative? Well, I don't know. Am I talking about how much energy is in the spring or how much energy something lost compressing the spring? We're being asked to compare this number to this number. Doesn't care about the negative sign. Now, they're specific. You need to figure out the percent change to go from 2.8 to 2.92. Now, to me, that would just be 2.8x equals 2.92 and figure out what x is. This would be the percent change. This would actually be over 100%. So the percent change would be the percent part above 100%, whatever that is. So technically, I'd only give the decimal answer as my percent change. But I think if you tell somebody it changed by 100 and whatever percent, they would understand what you mean. Does everybody know what I'm saying? I don't know what 2.92 divided by 2.8 is, but I'm pretty sure it's over 100. So what is the percent? What's the number? 1.04. So it's 104%. How would you say percent change here? Would you say a 4% change? 4% increase? That's one way to say it. Or you can say that it changed by 104%. All of these are valid ways of describing a percentage or a percent change. All right. Done a couple homework questions. I'm not testing calculus tomorrow though. So, but I'd be more apt to do something like this. And just let it be known that I'm parroting off what you've already done. So you should be able to use information you already have for this. That 2 kilogram ball from earlier, I have retracted the ball against a spring. I'm going to shoot the ball up the ramp. I would like the ball to go to the same 0.7 meter spot that we found in our practice quiz earlier today. The spring has a spring constant of 200 newtons per meter. How far back would I have to compress the spring in order to launch the ball to successfully make it to this height? Now, if you know what to do here, you understand that I've not asked for very much. But some of you are new to this, probably see this as a fresh problem. It really isn't. So I'm not actually asking this as a quiz, but you guys who are learned, you should run off and do this without any difficulty. You guys who are new to this, I want you to pay attention to what I'm about to say because you need this information. Right now, where's the energy in this system? I need you to understand this because this is the accounting for the energy. Is the energy in the ball? Is the energy in the incline? Is the energy in the spring? No. The truth is, the energy is in the spring ball system. It's important to understand that the spring can't be compressed without the ball being there. So technically we say that the energy is in the spring ball system. But I think most of us can agree that the energy is in the coils of the spring. As the spring returns back to its original shape, it's going to push on the ball. We could calculate the work done on the ball by dealing with it as an integral. But luckily for us, the spring force is a conservative force. Now, this is where I can state that the change in kinetic energy of the ball is going to be equal to the total work stored in the spring. I can state that because the spring is going to do work on the ball, and the spring is going to do the amount of work for the energy it has stored in itself. So instead of calculating it using calculus, I'm going to state that the energy stored in the spring is 1/2 kx squared, which currently is 1/2 200 d squared. Now, this is just going to change the kinetic energy of the ball. But we know how much kinetic energy the ball had when it made it to the 0.7 meters mark. We could use that. We have that knowledge. So we can go back and figure out, well, how fast was the ball going earlier? And I could use that to figure out how much kinetic energy the ball needs to have to make it to that 0.7 meter mark. By the way, how fast does this launcher have to launch the ball? How many? So 1/2 times 2 times 3 squared minus 0 has to be the change in kinetic energy of the ball as given to it by the spring. Now, this, not hard. I don't care what the answer is. I do want to at least say a few words about it. You should expect spring constants to be big numbers. They generally are. Usually, we don't want springs to compress very much. So remember, spring constants in newtons per meter. This ball is only 20 newtons. If I put the ball on the spring, I don't expect it to compress an entire meter. We generally expect springs to stretch just small amounts. So spring constants tend to be really big numbers. 200 is way on the low side of a spring constant. Generally, spring constants are in the thousands. On your car, tens of thousands. Now, you sit in your car, you put several hundred newtons of weight on your car. How far does a car sink? A centimeter or two, maybe? So spring constants tend to be very big numbers. You should expect the values for displacements of a spring to be relatively small numbers. Now, this is not the problem I want you to do. What if I wanted you instead to have the ball go 2 meters up the incline? How far back would I have to pull the spring now? Now, I want to talk about this from the standpoint of something different. I want to add something to our conversation. And it has to do with energy and accounting for the energy. I think most of you realize that one way we could do this is to figure out how much spring energy there is by 1/2 kx squared. Use that as the work done on the ball to find the change in kinetic energy. this would give us the velocity of the ball. And then use this to figure out how much work will be done by gravity on the ball. Because isn't this what's going to happen to the ball? The ball is going to start at rest, the spring's going to push on it and give it kinetic energy. Then the ball is going to encounter the hill, and gravity is going to take that energy away as the ball rolls up the hill. You are accounting for the energy. Do you not notice that this energy has to equal this energy, and that has to equal this energy? That we are accounting for the energy. So there's actually no reason to calculate the kinetic energy. Why stop at the middle step? Why not just realize that it has to be the same amount of energy in the ball when it's at the top of the ramp as there was in the spring before the ball was launched? This concept is known as conservation of energy. An accounting of energy allows us to stop always thinking about what is doing work and consider the flow of energy as a means of figuring out how our object behaves in nature. The ball is receiving energy from the spring. It's then having that energy taken away by gravity, but it's the same amount of energy all of the time. So instead of always figuring out work, we can account for the energy, maintain a status of looking at where the energy might be at different points, and arguably then cut out the middle steps when necessary. This problem allows us to cut out the middle steps. I can state right from the top that, all right, if I use what I did before, I'm going to have 1/2 times 200 times d squared, the energy stored in the spring. This has to equal, well, the weight of the ball, 20, times how far up the ramp it goes, d. Now here's where it gets a little tricky. We did the cosine of 130. That's going to make that right side negative. But do you recognize that's because we're taking the energy away from the ball? And this part was giving the energy to the ball. If I'm just accounting for the energy, I can kind of look at the absolute value here and recognize that it's got to be this amount of energy equal to this amount of energy. Oh yeah, and this is 2 meters. And just kind of ignore that for a minute. I'm not really ignoring it. This was added to the ball. This has to be taken away from the ball for it to be equal to, well, 0. So it zeroes out. The ball had 0 kinetic energy at the beginning. It has to have 0 kinetic energy at the end. I'm accounting for all of the energy. So the real question is, I mean, cut out the negative part of the 130, not the value, but the negative part of the 130.